Well, welcome to this seminar talk. So I was challenged with explaining all of electromagnetics to college freshmen in less than an hour. I accepted that challenge. I don't know how good a job I did. Maybe you can let me know, but here's my best to explain all of electromagnetics to a college level freshman. And you have not seen all of the math or all of the concepts, and it seems like this might be a difficult task to do. So what I've tried doing is doing all of this through pictures and animations and not math. Now, I do throw some equations up, but I'm not doing that for understanding. I'm just doing because I think you might be curious to see what some of these equations look like. But otherwise, I'm going to do all of my explanations through pictures and animations. So I'm calling this talk The Amazing World of Electromagnetics. Because I love electromagnetics, I think it is the closest thing to actual magic that we have in science. If you want to learn more about electromagnetics, computation, computational electromagnetics, career development, career advice, and other things, check out my website at empossible.net, especially if you like to learn in the same sort of visual way that we're doing here. I hope you enjoy this. So here's how I've organized this. First, we'll just talk about the electromagnetic fields and then the equations describing them called Maxwell's equations. We'll then move into electromagnetic properties of materials. We'll then talk about electromagnetic waves. With that background, we're ready to tackle a lot of different things. We'll talk about how waves reflect and refract from objects. Refraction is the bending at an interface. We'll talk about something called diffraction gratings. We'll talk about waveguides. We'll talk about filters where we can remove some frequencies and pass others. And we'll talk about antennas. So let's dive into this. Electromagnetic fields and Maxwell's equations. Well, these are the four Maxwell's equations, and this is a great place to start our conversation. Supposedly, these four equations describe all of classical electromagnetics. It explains why we see ourselves in a mirror, why we see rainbows, and things like that. Just looking at these equations, no, it's not obvious to me any of that. And don't worry, you don't need to look at these equations or understand them. I'm just showing them here for your interest to see what will be coming your way if you decide to study electromagnetics. So let's get into these. First, we're going to discuss the terms that you see in these equations, and then we'll describe the equations themselves. In Maxwell's equations, it may seem strange that we have two different electric field terms, E and D. And in fact, I'll admit for many years, I did not really understand the difference between E and D, but I thought this has to be so simple that I was embarrassed to ask the question. I never asked the question. Many years later, when I finally figured out what the difference was between E and D, it really opened up a whole new level of understanding of electromagnetics for me. And I like to use this as an example to students. If you have a question in your brain that you think is dumb, you're embarrassed to ask, go ahead and ask it because it really can hold you back. Anyway, here's the short story of the difference between E and D. There are two ways that we can have electric energy. First, we can have electric energy in the field itself. We know this because we have electromagnetic waves in outer space, and we know that they can deliver energy. There's no matter in outer space, so there has to be energy in the field itself. Call this the electric field intensity, and we'll give it units of volts per meter. So this is the term most closely associated with voltage and also force, when electric fields put a force onto things. Now, the second form of electric energy is electric energy that can be stored inside of matter. So imagine we apply a voltage across some block of material, a dielectric. Well, that voltage creates an electric field, and that electric field puts a force on charges. That will pull the electrons one way and the nuclei the other way. And if we're not pulling too hard, we're not going to break the electrons away. But what ends up happening is we stretch the spins of these electrons. And it's like a mass on a spring. Those electrons want to spring back to their default position. And so that is what is storing energy at the atomic scale in the form of displaced charge. When a material has all of these stretched electron clouds, we call it polarized, and we can give it a vector, well, P, and that's because it has this pulling, the stretching has a direction. We'll give it units of coulombs per meter squared, and the coulomb is the unit of electric charge. The electric field term D is the all-inclusive term. This is the electric field term that includes both forms of energy, the energy that exists in the field itself and the electric energy that we can store in matter. Now this will have the same units as the material polarization, coulombs per meter squared. Now the electric field intensity does not have those same units, so we have to multiply it by this constant that we call the free space permittivity. And that gives this outer space vacuum electric energy the same units as if it was displaced charge, and that lets us add E and P to get our D term. And there's a whole set of science and amazing things that we can understand when we start looking at this material polarization, and unfortunately, I just can't get into that here. There is a very similar story to tell about the magnetic fields. There are two magnetic field terms that we find in Maxwell's equations. And that's because there's two ways that we can have magnetic energy. The first, we know that there's energy in the field itself. Call this the magnetic field intensity. We'll write that as H, and it has units of amperes per meter. And amperes is the units of electrical current. So this magnetic field is most closely associated with electric current. We can also store magnetic energy at the atomic scale. When something is storing magnetic energy at the atomic scale, we call that magnetized. And so we'll write this as a vector called the material magnetization. It has units of Webers per meter squared. Now, there's no such thing as magnetic charge, but if there was, the magnetic charge would have units of Webers. Now, at the atomic scale, the electron orbits can be limited to more of a donut pattern. And whenever we have spinning charges like this, we'll learn this a little bit later in Maxwell's equations, whenever there's spinning charge, we get a magnetic field induced down the center of that rotation. And that's what I'm showing with these red arrows. Now, ordinarily, these are oriented all randomly. If we apply a magnetic field H to this, they will tend to line up. Now, they want to spring back to their default position, and so that mass on a spring model again comes up, and we're storing magnetic energy at the atomic scale. The magnetic field term B, this is the all-inclusive term that includes both forms of magnetic energy, the energy in the field itself and the energy stored in matter in the form of these displaced magnetic dipoles. It's called the magnetic flux density, and we give it the same units as the magnetization, Webers per meter squared. Now, the magnetic field intensity, H, does not have those units, so we have to multiply it by what we call the free space permeability to give it the same units so that the energy in the field has the same units as tilted dipoles. There's a J term in Maxwell's equations. This is an electric current density. So if there's electricity flowing down this wire, the total amount of flow we would call the current, and we would write that as I. But really, the flow of charges is distributed throughout the entire conductor. So it makes sense then that we could talk about some kind of spread out or distributed current, and that's what we call the current density. And it has units of amps per meter squared. And essentially, if we were to add all of this up, we would get the total current. And that's what this strange looking equation says over here. Remember, I'm just putting the equations up more for curiosity, that you can see what equations are coming to you in electromagnetics, but you don't have to understand the equation to understand what I'm talking about. So that's the electric current density. The last term we'll talk about is the volume charge density. And think of charge like a cloud, and that's what I'm showing over here on the right, sort of this speckly cloud. And where you see the deepest red, that's where there's the most charge. And so, but charge is distributed and sort of spread out, so it makes sense to talk about a charge density. And again, if we were to go ahead and add all this up, we would get total charge Q. And here's a fancy equation over here that would do that. Total charge Q, we're adding up over the volume, our charge density. We're finally ready to move into Maxwell's equations. And I don't know if there's a particular order to these, but this is the first one we will discuss. And this is called Gauss's law for electric fields. So if we have a charge, call it a positive charge, the electric field lines will emerge straight out of that. Kind of looks like a porcupine or maybe a pufferfish or something like that. Now, if I make this charge more, stronger charge, we end up seeing more field lines, a greater density of field lines. And when these field lines emerge from a point, that is called divergence. Those lines appear to diverge from where the charge is. And so that's exactly what the first of Maxwell's equations say. This is a vector calculus thing. And what this is doing is it's calculating the divergence of the electric flux. And it's saying if the electric flux is diverging from a particular point, well, there must be charge there. And that's the first equation. And it makes sense. If we were to somehow also add up all of these field lines, we could figure out how much charge was in there. So this equation actually works both ways. That's Gauss's law for electric fields. We have Gauss's law for magnetic fields, but there's a different conclusion here. There is no such thing as magnetic charges or magnetic monopoles. So if we calculate the divergence of the magnetic flux, that has to be zero. Now, since there is no divergence of the magnetic flux, that really means magnetic fields can't start and they can't end, yet they exist. The only way this is possible then is if the magnetic fields form loops. That way they have no beginning and end, yet they can exist. And that's exactly what happens. Magnetic fields only ever form loops, and the fundamental reason is there's no magnetic charge. Now we move into Faraday's law. And here's some more weird math symbols that we don't have to recognize. Looks similar to when we were talking about divergence, but instead of a dot, there's a cross here. This is called a vector cross product. What this is doing is it's calculating something called curl, and it is the tendency of the electric field to circulate around some axis. And this circulation equals, and this d dt symbol here means it's how much the magnetic flux is changing over time t. So if the magnetic field is changing with time, that is going to cause an electric field to circulate around it. And it works the other way around. If somehow we can start by making a circulating electric field, that will cause a magnetic field around through the axis of that circulation. And that's what we're looking at over on the left. The electric field is shown in blue, the magnetic field in B. And we can see if B is increasing at a constant rate, we get a constant electric field. Whereas when it changes and accelerates, we get an electric field that changes. And the faster the B field changes, the stronger the electric field that it induces. But what to remember is time-changing electric fields circulate around time-changing magnetic fields. Here's a very similar law, and this is called Ampere's circuit law. And so we have a del cross H. Similar to last slide, so we are calculating the tendency of the magnetic field intensity to circulate around some axis. And what this equation is saying is if there is a magnetic field circulating around some axis, there has to be either an electric current or an electric flux that's changing over time, or some combination of both. And I've illustrated them both separately down below. We might have a current, and the magnetic field is simply proportional to the current. Nothing here has to change with time. We can have a steady electric current, and we'll have a magnetic field around it. Now, interestingly, if we were to try that one the other way around, it doesn't quite work. We actually need to change the magnetic field with respect to time in order to get a current. Now, if we look at the other term here, if we have an electric flux, we'll get a magnetic field circulating around that when the electric field is changing. And the more quickly it changes, the more strongly we'll have that magnetic field. And this is reversible. We can start with the electric field, we'll get a circulating magnetic field, or if somehow we could create a circulating magnetic field, we would get a time-changing electric field right through the axis of that circulation. So the big conclusion here is that magnetic fields circulate around currents and time-changing electric fields. So that's it. We have stepped through all 4 of Maxwell's equations. And in that sense, they're quite simple. The first equation said that electric fields diverge from charges. Magnetic fields can't diverge, so they have to form loops. Faraday's law says we'll have electric fields circulating around magnetic fields, and Ampere's law said we're going to have magnetic fields circulating around electric fields or currents. Now notice, none of those equations are called Maxwell's equations. They're called Maxwell's equations as a group, but other people invented those. Now, Ampere's circuit law was just Ampere's law. And what Maxwell did was add this term. That's called the displacement term. It wasn't quite known at the time that a time-changing electric field would induce a circulating electric field. So Maxwell added that term that unified the electromagnetic equations, and that let him derive a wave equation. From that, he could predict the speed of light analytically. Of course, they had measured it before this, but suddenly there was a mathematical basis, and Maxwell unified this, and that's why the group of equations is called Maxwell's equations, even though he's not responsible for any of those 4. Electromagnetic properties of materials. We will start this conversation by looking at Maxwell's equations again. And let me ask a question. Where are the material properties in these equations? That's rather unusual. And in fact, Maxwell's equations don't directly tell us how the fields interact with matter. Maxwell's equations is more about what induces electric fields. How do we get them, right? Time-changing electric fields give us time-changing magnetic fields and vice versa, or charges will create electric fields diverging from them, but they don't tell us how the fields interact with materials. And if you're ever talking with an electromagnetics person, sometime you could very likely win a bet by telling them, hey, Maxwell's equations don't tell us how the fields interact with materials. And they will think you're crazy, but in fact, they don't. There's no material parameters in here. So I would say Maxwell's equations is actually an incomplete set of equations, and we need more information to analyze problems. One of the things that's missing is what's called the constitutive relations, and this is where the material properties come in. The first equation describes the electric response of materials. Remember, this electric flux was the all-inclusive term that included both the vacuum energy and the electric energy stored in matter. We can lump this into an easier equation that just relates D to E through this variable epsilon. That's a Greek letter epsilon. And this is called the permittivity, and it measures how well the medium can store electric energy. And it's accounting for both the vacuum of space and matter. So in the vacuum of space, how is that? Well, the vacuum of space itself is not storing the energy, but the energy is in the field itself. However, if there's also matter, we can have energy in the field and displaced charge. The permittivity includes all of that in a single number, and it's the ability of that medium to store electric energy. And so D and E are related through that. The second of the constitutive relations describes the magnetic response of materials. And here, B, this is the all-inclusive a magnetic field term that includes both the vacuum energy and the magnetic energy stored in matter, and it directly relates B and H through this constant called the permeability. And the permeability is how well a medium can store magnetic energy. So vacuum can store magnetic energy in the field, and matter can store magnetic energy in terms of these displaced magnetic dipoles, if you will, or these tilted magnetic dipoles. Those are the constitutive relations. These describe how the electric and magnetic fields interact with matter. And so in combination with Maxwell's equations now, we have a complete description of electromagnetic fields. Now here's a bummer. Nature only gives us so many different types of materials. This permittivity is really always has to be greater than 1. And while there are certainly cases where they can be much higher values in a practical setting and at higher frequencies, 20 is about the highest I've seen, and I might even be able to write a 10 there. So we're rather limited in the range of values for permittivity and permeability. Later, we'll talk about this refractive index. That's how much a wave slows down relative to the speed of light. So if refractive index is 2, the speed is traveling half the speed of light. And this is always greater than or equal to 1 because we can't have waves traveling faster than the speed of light. That's sort of a fundamental limit in nature. And some of the highest values I've seen are around 5. So nature limits us here, although there's some very rare examples where maybe we can push that. So along comes this concept, and this started, I would say, in the 1990s, this concept of metamaterials. Meta is a prefix, meaning better than or beyond, and of course materials is materials. So we're talking about something that is beyond ordinary materials. And what's really cool, we can design these little metallic structures and all kinds of different designs here, but this behaves as if it has an effective permeability and permittivity. And in fact, we can get really extreme values and strange values and do some really, really cool things that we just can't do with naturally occurring materials. And so this is a huge area of electromagnetics right now and lots of cool things. One of the most famous, this was something achieved by Duke University, invisibility and cloaking. And how do we render an object invisible? Well, you have to have a wave when it approaches that object that bends around and comes out and creates a wavefront that's perfectly in phase again, right? This wavefront on the output looks like this wavefront on the input. And so you can't tell that anything was here. And so we have to do that to achieve cloaking and invisibility. Well, the stuff here that bends the fields has very crazy values of the permeability and permittivity. And the only way we can do that is through this concept of metamaterials. So here's Duke University's actual cloak, the first ever cloak, and you can see this periodic arrangement of these little metal elements. And one thing you can't see, there's also these straight metal bars here and there. It's kind of hard to see in this picture. But that was the first ever invisibility cloak. Let's talk a little bit more of what it takes to do an invisibility cloak. So let's say we have a triangular object sitting in the vacuum of space. That means the wave outside is traveling at the speed of light, and supposedly nothing can travel faster than the speed of light. Well, think of what has to happen to a portion of wave in here. Well, it has to travel a farther distance, right? Because it's bending around this triangle and coming out at essentially along the same path that it came in at to form these flat wave fronts on the other side. Well, if this portion of the wave has to travel a farther distance, but yet come out with the same timing as part of the wave, outside this cloak, doesn't that mean it has to travel faster than light in there? And the answer is, in fact, yes. And so metamaterials has really led to a lot of controversy in the scientific community, and it allows us to bend rules we didn't think could be bent before in an absolutely fascinating field. And there's really some cool articles out there where the scientists literally argue and call each other names and stuff, and it's quite funny. I enjoy that, I think. But I love controversy in science because that means we're on to something new. And so cloaking and invisibility introduces this concept of faster than light travel. Is that really possible? There's also something called left-handed materials. We're all used to, maybe we put a spoon in water and we see this bending, or we put a stick in the water, it appears to bend a little bit, and that is called refraction. Well, metamaterials can actually cause something called negative refraction, where the light rays bend in the complete opposite direction that we would think that they would. So on the right, sort of a simulation of that, we can see a beam of light coming in, and it actually bends in the opposite direction. And so if we had water that was left-handed, or also we'll say a negative refractive index, well, the spoon would look like this. That's completely crazy. And that's because of the light waves bend opposite. That spoon actually appears to be coming from a different place than it actually is. Another really weird thing happening, and we're used to these wave fronts. Notice they're moving in the direction of the beam up here in this ordinary medium. But now down here, if we were to look at this with our eyes don't see the wave fronts of the wave. We're not quick enough to do that. So the beam looks as if it's going off in this direction, and it is. But if we were to somehow visualize the wavefronts are actually moving in this direction. So the direction of the ripples of the wave is different than the direction that energy is actually moving. And this seems completely crazy. Here's an analogy. So imagine you're standing up and you spin in a circle real fast, so 20 times. You get yourself very dizzy. And then you look at an object off in the distance, and I tell you, walk towards that object. Well, your body's facing that object. You're meaning to go that way toward the object. That's the ripples, yet you're dizzy and you're walking off to the side. And so electromagnetic waves inside some of these metamaterials act in a very different way. The ripples are trying to go one way, but the energy actually goes a different way. And so we can do all kinds of cool manipulation of waves inside these things, and I wish I could get more into that. We can have materials that are anisotropic. That's kind of a big word. And what that means is that the material properties change depending on the direction of the wave. And so what I'm trying to visualize over here we have a wave vertical and it's traveling more slowly and the wavefronts are compressed. But in the A or B directions, look how much faster that wave is traveling and it's more spread out. And so if different directions have different properties, one cool thing that can happen is something called double refraction. So here's a crystal that has two different refractive indices. We would call that birefringent. And if we put that over top of an image, notice we see two images. And that's because it's refracting in two different directions because it sees two different refractive indices. And in metamaterials, we can do a very similar thing. So all kinds of weird, cool things that can happen when we look at the material properties. Electromagnetic waves and polarization. We need to think about how electromagnetic waves propagate. And let's go back to what we learned when we talked about Maxwell's equations. And so we start off with a time-changing electric field. What do we know about a time-changing electric field? That time-changing electric field will induce a circulating magnetic field that's also changing with time. This was called Ampere's circuit law. So we now have a time-changing magnetic field. Let's go ahead and zoom in on one of the magnetic fields to the right of where we had the electric field. And so we have a time-changing magnetic field at a slightly different position. Well, what do we know about time-changing magnetic fields? Time-changing magnetic fields will induce a time-changing electric field circulating around it. So we started off with a time-changing electric field that induced a time-changing magnetic field that has now induced yet another time-changing electric field. So let's zoom in on one of the electric fields just to the right of that magnetic field. And we're back to a time-changing electric field at a slightly different position. That time-changing electric field induces a time-changing magnetic field circulating around it. And that time-changing magnetic field will induce a circulating electric field, and so on. And I kind of, in my mind, envision these as a linked chain. And we can also imagine propagation is going to happen in a bunch of different directions at this point. But that's how waves propagate. Time-changing electric field induces a time-changing magnetic field, which induces a time-changing electric field, which induces a time-changing magnetic field. And so there's sort of this exchange of energy between the electric and magnetic fields. And that's why waves propagate. And that's also why there is both an electric and a magnetic field component to a plane wave. So back to Maxwell's equations, which I promise you don't have to follow or understand. But what we saw is it's these curl equations in conjunction with the constitutive parameters, but it's the curl equations that predict waves, right? The time-changing magnetic field induces a time-changing electric field circulating around it, and a time-changing electric field induces a time-changing magnetic field circulating around it. It's the interaction of these two. So mathematically, if we take these two equations and combine them, we get what's called the wave equation. Now, it was Maxwell that derived the electromagnetic wave equation for the first time. That wasn't possible until he added that term. Ampere just had a magnetic field circulating around a current. Well, it turns out a magnetic field will also circulate around a time-changing electric field. Once this was added, Maxwell was able to derive the wave equation, and the wave equation for other waves was known for a very, very long time. And that allowed Maxwell to compare this to the historical wave equation. And he looked at this group of terms and was able for the first time to derive the velocity of an electromagnetic wave. And that was a huge deal at the time. Today, in modern days, that maybe seems kind of boring or simple. But at the time, that was quite exciting because they could never before explain the velocity of an electromagnetic wave. But once it was known to be truly a wave, they had the wave equation, out came the velocity. So let's try to picture an electromagnetic wave. And to be honest, I have not come up with a good way to visualize an electromagnetic wave. But this is the traditional way. So we're talking about a wave traveling in the z direction. There's both an electric and a magnetic field. And in fact, the electric field always has to be perpendicular to the direction the wave is going, and so does the magnetic field. And even more, the electric and magnetic field have to be perpendicular to each other. So the electric field, the magnetic field, and the direction of the wave, all three are all perpendicular to each other. So we're drawing the electric field oscillating, in this case, in the x direction, even though the wave is traveling in the z direction, and the magnetic field is oscillating in the y direction. Now notice how much smaller I've drawn the magnetic field than the electric field. And in fact, the magnetic field is 3 orders of magnitude smaller than the electric field. You wouldn't even see it if I drew this to scale. So I sort of had to lie and exaggerate the amplitude of the magnetic field so that you would see it. Now, the reason I don't like this type of visualization is it seems to imply 2 incorrect things. One, that something is only happening exactly on this z-axis. And that's not true. We're talking about a plane wave that is of infinite extent in the x and y direction. So it's much more like these sort of flat pieces of paper, fuzzy, cloudy paper moving along the z-axis. Now, if I try to visualize that, here's what that looks like. You know, we have electric and magnetic fields of infinite extent in the x and y direction. They're all oscillating. But this is crazy to look at. We don't understand it. And so we have to go back to what we saw on the previous slide. The other thing, when we draw vectors, it seems to imply, let's look at this little vector here. We're talking about something happening at a single point. But because we draw the vector extending away, it seems to imply that this phenomenon is spread out. Now, the phenomenon is spread out, but when we draw the vectors, we're talking about something that is at an infinitely small point. And so all this together, electromagnetic waves are very, very difficult to visualize. We want to create a virtual reality environment that will let you interact with electromagnetic waves. But one big problem we're facing is, how do you visualize an electromagnetic wave? I think there's just many more dimensions of information there than our eyes and brains can process. So that I know of, there has not been any real good visualizations of electromagnetic waves. But what was on the previous slide is traditionally how it's done. Let's talk more about this refractive index. So the refractive index was known well before we knew that light was a wave. We just saw light bend at interfaces, and they came up with this mysterious thing called refractive index that was associated with the medium that described the bending. Today, we know what causes the bending has to do with a change in speed across an interface. That's something we'll talk about later. So the refractive index n is the factor by which a wave slows down relative to the speed of light in vacuum. So this constant, C naught, this is the speed of light in vacuum. And it's roughly 3 times 10 to the 8 meters per second. That's super fast. So the speed of the wave is the vacuum speed of light divided by refractive index. So if refractive index is 2, the speed of the wave inside that medium that has refractive index 2 is half of the speed of light. Now notice here that the frequency of the wave does not change. That remains constant. And that's what I'm trying to show with these green dots. The speed that these things are going up and down is the same on both sides. So frequency never really changes. But certainly the speed of the wave changes, and also the wavelength. Notice the slower wave is more compressed. The faster wave is more spread out. And when we start talking about refraction or the bending at an interface, that is going to be very important. Wave polarization. This is where we're reusing that word polarization. So we're not talking about material polarization now. We're talking about the polarization of an electromagnetic wave. And what that is, that's the behavior of the electric field of a wave. So here we're drawing a wave where the electric field is oscillating purely along the z-axis, sorry, the x-axis. The x-axis is a straight line. This is a linear thing. So we call that a linear polarization. And by the way, these little blue fuzzy regions out here, I'm trying to draw this wave of infinite extent in the x and y directions. And an electromagnetic field is much more like a cloud than anything else. And I'm trying to convey that and still struggling. And so hopefully you can appreciate that it's struggling. But this polarization looks the same no matter where you are in this wave. But just because we can only draw so many things at the same time, I'm only drawing the polarization along the z-axis. But that electric field is perpendicular to the direction the wave is going. Another thing that can happen is that the electric field can spin. And if it traces out a circle in its path, we call that a circularly polarized wave. Now, why is polarization even important? Well, if we have a polarization that's perpendicular, so let's say we have an antenna in a remote control airplane that is receiving electromagnetic waves polarized in the x direction, but our handheld controller has an antenna that's emitting something polarized in the y direction. Well, guess what? That antenna is not going to receive your signal. You're going to lose control of the airplane and it's going to crash. And so there's a good example of why polarization is important. But it turns out that devices behave differently depending on polarization. Lenses will focus differently. Diffraction happens differently. All kinds of weird, crazy things. So anyway, this is called circular polarization. Another thing that can happen is that the electric field traces out an ellipse. And so this is called elliptical polarization. And I would say 99% of all possible polarizations are elliptical. In fact, linear and circular are just special cases of an elliptical polarization. Let's say the width of this ellipse along this short axis here goes to 0. Well, this would be oscillating along a straight line, tilted off of the x-axis, but it would still be oscillating along a straight line. It would be a linear polarization. Now, if the width of this ellipse was the same, wide as it is tall, that would be a circle. That's circular polarization. So linear and circular polarizations are special cases of elliptical polarization. We tend to like things to be linear or circular. It's very rare that we actually want something to have an elliptical polarization. Armed with the idea of polarization, now we can understand how polarized sunglasses works. It turns out when light is reflected off of a smooth surface like glass or water, even though we might have all polarizations being equal when it hits that surface, when it reflects, notice this polarization in the red direction is much stronger than the polarization in the X direction. In fact, the difference is even stronger than that, but I wanted to at least visualize the wave. So we design glasses that can block one of those polarizations. And in this case, it will be blocking what gets reflected more strongly, this red polarization, and what gets through is the blue polarization. And so this reduces glare off of surfaces. And this picture to the right, I think, explains that also better. So, our eyes would see this. We see this huge reflection off the water, and even other things tend to reflect one of the polarizations more strongly. And if we go ahead and we block that, now we can see things with a bit more contrast. We can see through water. So fishermen love wearing polarized sunglasses. Another crazy thing that happens when you wear polarized sunglasses, if you look at a liquid crystal display, that actually uses polarization to form its image. And if you tilt your head to the side, to the left, to the right, you'll see those liquid crystal displays turn black, and then you'll see it again. So maybe it's like the GPS in your car or an LCD display on a wristwatch, and that's all a polarization effect. If you go to the movies and watch a three-dimensional movie, the glasses you're wearing are manipulating the polarization of the light. So polarization is hugely important, and you've already felt the effects of that, whether you knew it or not. Reflection and refraction. So here we have two different mediums. Let's call this air up top, and let's call this, water or glass down below. And so what happens when an electromagnetic wave passing from air hits this glass or water or some other material? And what we're doing is we're characterizing the first material by its refractive index N1 and the second material also by its refractive index N2. So what happens? Well, two things can actually happen. First, we can have reflections. Second, some of that can transmit. And notice the angle of that transmitted wave is a little bit different than the angle of the incoming wave. And that bending is called refraction. So in general, both happen. But what you'll see me do in the coming slides is I'll turn one or the other off just to simplify what we're looking at. Now, the angles of reflection and refraction are pretty easy to calculate. The angle of reflection is equal to the angle of incidence. So that's why I have both of these angles labeled theta 1. That's the Greek letter theta, and that's used pretty ubiquitously out through all of science and engineering for angle. And so think about it, if you're playing billiards or pool and you bounce a ball off of the bumper, it comes off at the same angle that it hit the bumper. That makes pretty intuitive sense. Now the angle on the transmitted side, that's a little different. The angle changes. And this is called Snell's law of refraction. And here's the equation describing that. So it has our angles, theta 1, that's the incoming angle. It has theta 2, that's the outgoing angle. And it has the two different refractive indices. So clearly, speed of the wave has something to do with why that wave bends. Let's think about why this wave bends. So what we have here is an animation of our incoming wave, and on the transmitted side, I'm experimenting with waves at a bunch of different angles, and I'm just kind of swaying the angle back and forth. And this gold arrow here is showing the actual correct angle, and the green arrow is showing the direction that I'm trying. Now, in electromagnetics, we have what are called boundary conditions, and it's what's happening at the interface here. And it turns out we need the field to be continuous across this interface. So we need whatever it looks like right above the interface, it needs to look the exact same way below the interface. And if we look at these two fields, that continuity only happens for one special angle. And the continuity is when the red lines up here continue to the red lines below, and the blue lines continue to the blue lines below. And if we take a look at that, that only happens when the green arrow is in the direction of that gold arrow. So let's go ahead and freeze on that magical angle. And what you can see is, yes, the red lines and blue lines, they're both continuous across that interface. That's why refraction happens. The wave in the first medium is traveling faster. It's more spread out. Evidently, it has a lower refractive index. Down here, it's compressed. It's traveling more slowly because it has a higher refractive index. So since they repeat more densely down here, but yet it still has to match to what's happening above, the angle has to change so that right along the interface, the repetition's just as quick, and the red lines connect to red lines and blue lines connect to blue lines. So that's why refraction is happening. It has to do with the speed changing and the field needing to be continuous across that interface. In this animation, we're looking at a wave going from a low index medium to a high index medium. Its low index is traveling faster, so the wave is more spread out. In the high index medium, the wave is compressed, and so we get refraction. Now notice as we're changing angle for the incoming wave above, we always get a smaller angle in this medium below. And so that's typical. The smaller angle is always in the higher index medium. Another thing that happens is this wave always transmits through the interface. Now, of course, there's some being reflected. I'm just not showing that here. Something much more interesting happens when we reverse this, and we have a wave going from a high index medium into a low index medium. Let's look at that next. Here is this case where we have a wave in a high index medium that is incident onto a low index medium. Remember, the angle is always smaller in the low index medium. So what happens then when the wave becomes very large in this high index medium? Well, it turns out it becomes impossible for there to be a wave over here in the second medium. And what we can see, there's a magical angle right when this disappears, and that is called the critical angle. So when our incoming wave is at an angle greater than the critical angle, it's called cut off. That wave does not exist down here, and it turns out it will be completely reflected, and that's called total internal reflection. It is also what's responsible for guiding waves down fiber optic cables. The refractive index at the center of a fiber optic cable is higher than the glass surrounding that, and so the light experiences total internal reflection and stays guided down the core. Now we need to talk a little bit about how much reflects and transmits. And this is described by another set of equations called the Fresnel equations that I'm not getting into, but here I've animated the Fresnel equations. So the green arrow is the incoming wave, And the red and the blue arrows are showing by the size how much is getting reflected and transmitted as a function of the angle. You'll also notice that I have two pictures here, and that's because there's two possible polarizations for the incoming wave, and those two polarizations reflect and transmit differently. Now we will notice something sort of interesting for the TE polarization. Notice there is a special angle where this reflected wave goes to zero. That is known as the Brewster's angle, and it's one thing that could be used to make a polarizer. When this incoming wave comes in at the Brewster angle, the only thing that can get reflected from the interface is the TM polarization. So it's a way that we can use to remove the TE polarization. There's a neat device called a metasurface. We've just learned about the law of reflection and the law of refraction. Well, a metasurface is generally an array of little tiny metallic elements, and the metallic elements are spaced so closely that they're smaller than the wavelength. And what happens is we can modify the law of reflection and the law of refraction to change that, and we can reflect or refract a wave into any direction that we want. And what's happening is these little elements, depending on their pattern, they're changing the phase or the timing of the signal coming in. And by changing the timing, and we do that differently across this whole device, we actually can change the angle of what gets reflected or transmitted. So that's the purpose of a metasurface. And another way that we can use metasurfaces is not only to change the angle, but also the amplitude and control the amplitude profile. Maybe we have a nice plane wave coming in and we want a smiley face looking beam coming off. Metasurfaces can also do that. A device that we're all familiar with is a lens, and this is a device based on refraction. At the front of our eyeballs, we have a lens, and that focuses the light on the back of our retinas. And so right here at the focal point, we form an image. So the way the lens works, let's go ahead and animate this. We have a nice flat sort of front of light coming into the lens. When it passes through the lens, it's thicker at the middle, and it delays that part of the wave more than the outside, so the outside gets ahead of it. And we get these spherical wave fronts, which cause it to converge and to focus. And so that's a lens. Coming into the lens, we have the flat wave fronts shown by these dashed blue lines. And on the other side, we have these curved wave fronts, which makes it focus. And as I mentioned, we'll form an image right here. So if this were a camera, this is the big lens up front, we would have our CCD array right here to detect that image. So another whole area of electromagnetics and optics is studying how those rays converge. If the rays don't converge correctly, that's called an aberration. And if you're a person that has to wear eyeglasses, that's because your lens is not forming images and you're getting aberrations, and so you wear corrective lenses over your eyes. One cool thing we can do is something called a diffractive optical element. It's really just the slope of the lens that bends the rays in a way that forms the lens. So we have a way to flatten our lens as long as we can preserve the slope, other except at these little steps, but we're preserving the slope, but we flatten the lens. So it acts the same way with a much flatter, more compact device. Diffraction gratings. First, what is a diffraction grating? So we're looking at a device here. Now imagine this being infinitely extruded in and out of the screen. So it's a periodic arrangement of bumps. Now this is going to be a simulation that you'll see. And what you'll see is a beam of light will be incident from the top. It will hit this diffraction grating. And of course, these little bumps will make the wavefront bumpy. And something kind of magical happens on the transmitted side. So let's go ahead and play this simulation. So it's chopping up that wavefront, looks all bumpy and crazy. But if we let those waves travel away from the diffraction grating, what we actually see is the wave has split into these discrete directions. And all of these discrete directions, these are called diffraction orders, and we even give them numbers. This is the 0 order diffraction order, and then we have the plus and minus 1 diffraction orders, plus and minus 2 diffraction orders. But the point is, a diffraction grating, when light hits that, it splits that into discrete directions. Now, if we were to shine white light onto a diffraction grating, and white light, of course, is composed of all the different colors of the rainbow, this is what would happen. We would still get diffraction, but if we were to look at one of the diffraction orders, if we looked at the +1 diffraction order, what we see is that the different colors of light actually diffract at a slightly different angle, and it begins to separate the light. So the +1 and -1 diffraction order, they work the same. But if we look down below, look at the spread for the +1 on the transmitted side. Then look at the spread for the +2 and the +3. What we can see is that those larger numbers, the higher order diffraction orders, actually spread the light out more. Now, this is very useful when we want to spread the light out, which we'll talk about on the next slide. Here's an example of this from nature. If you take something like silk or feathers that have very, very fine structures and shine light through them, you will see these kind of rainbowish patterns, and that's exactly what's happening. It's diffraction here through the feather, but the diffraction disperses the light. It spreads out the different colors, and we see these rainbow patterns. Now, very often, we can make measurements with light. We'll shine light through something, and that something will absorb certain colors and not others, and we can tell by that what's in that something that we're measuring. So one thing of interest is diabetes, and people want to shine light through blood so you don't have to poke yourself, and the glucose has a very recognizable absorption spectrum. In other words, it'll absorb certain colors and not others in a recognizable pattern. So in theory, you could shine light through somebody's finger and measure their blood glucose. And that's just one of many, many things. So here's how a grating spectrometer would work. This is one that at least was offered by a company called Ocean Optics. And so this is a fiber optic input, and you'd hook a fiber optic cable up to this, and the white light comes out. Now, we've shined it through a sample or something out here, and we want to see what colors make up that light. So the white light comes in, it bounces off of a mirror, and it hits a diffraction grating. Number 5 is the diffraction grating. And they probably choose one of the diffraction orders. Maybe it's the +1, maybe it's the +2 if they want to disperse the light even more. So the light begins to separate, bounces off another mirror, and all of this folding is to give the light distance so that it can spread out even more. And then it finally hits a CCD array, charge coupled device. That's the sensor that's in your cameras. And it's recording the light across this thing. So of course the little pixels absorbing light here are measuring red content, and then down here measuring yellow and green and blue and violet. And so there's probably hundreds of little pixels here, and you can plot the spectrum of light and make all kinds of very interesting measurements. So gratings are used all the time for that reason. Here's another really neat application of diffraction gratings, and this is called a Littrow grating, or maybe more correctly, the Littrow configuration. And what we'll do is we'll have broad light, so I'll just show that as white hitting the grating. And we designed this diffraction grating so that one of the diffraction orders reflects in the exact same direction that the light came in. But of course, it's a diffraction grating. It disperses or spreads out the light. And if we let this go far enough and we only detect a certain range of that, what we're doing is a filtering operation. We're removing, in this case, the red and part of the yellow light and all of the violet light, and only detecting the yellow or green. And if you imagine, letting this light go even farther or making the detector smaller, we can essentially have a mirror here that only reflects a very certain color. So this is a Littrow configuration of a diffraction grating. Many more applications of diffraction gratings, but we're rushed for time, so we're ending it here on diffraction gratings. Waveguides. Waveguides are pipes for electromagnetic energy. Waveguides fall into two broad classes. A slab waveguide, you imagine maybe having a metal wall at the top and a metal wall at the bottom, but otherwise it's open left to right. This guided wave, if you will, is only confined vertically, and it's able to propagate in any direction within that sort of slab, or the sandwich between these two plates. On the other hand, we have what are called channel waveguides, and I've drawn here sort of two slab waveguides mixed together, but what we see is we have a channel, and so the wave is confined both vertically and horizontally. There's only one direction for that wave to go, and it's down that channel. I think by far the most common waveguide in existence is an optical fiber. These are dielectric waveguides. There's no metals involved. It's easy to think how a metal pipe can form a waveguide, but maybe not as much for a dielectric waveguide. So these are optical fibers, and this optical fiber, it's about 100 microns wide. That's roughly the same size as a hair on your head. But in fact, the light travels down a much smaller region of that. So the bulk of the glass is called the cladding, and it's simply there to make it strong enough so that if you blow on it, it doesn't break. At the very center, in about the center 10 microns, is the core. And this has a slightly higher refractive index, a very, very slightly higher refractive index. But since the light is here in the high refractive index medium and it has a lower refractive index on the outside, that means there exists a critical angle where we will get total internal reflection and the light can stay trapped. If we inject light at an angle less than the critical angle, well, it actually escapes and it gets out into the cladding and probably escapes out of the fiber, and we'll see it glowing over whatever distance it takes for that light to leak out. So that's an optical fiber, and there are thousands of kilometers of this installed across the world. That's why we have such fast internet, so many television channels, and everything else. And the Nobel Prize was won for inventing the optical fiber. There's metal waveguides. These are not used for light, although people have talked about it. These are used more for radio and microwave frequencies. And it's used at when the frequencies get too high for something that can be transported on a circuit board, or the power is very high. And we use these metal waveguides. And so the metal here acts like a mirror, so it's a little bit more intuitive of why the electromagnetic wave would stay trapped inside these things and travel down the pipe. Now, the electromagnetic fields inside of a waveguide, they're not free to do whatever they want. They have to follow rules. They have to follow Maxwell's equations. And it turns out there's only certain pictures that the fields can look like inside of these waveguides. And we call these modes, or guided modes. So on the left, we're looking at one. We're looking at what the picture looks like. And I'm drawing the mode inside of the waveguide. Now, as that wave propagates, as the mode propagates, what we're seeing is basically a sine wave here, and it's going in and out of phase. But the overall picture really always looks like this. It's just accumulating phase, and it's a sine wave. It goes up and down as it propagates, and that's why it looks like it's flashing. But the picture of the mode is actually the same. And waveguides can support multiple modes. So here we see a different mode in that waveguide, but the concept is the same. The picture of that mode stays the same. It just propagates down the waveguide and kind of goes in and out following a sine wave. What we tend to want to do is take the size of the waveguide and shrink it down until it only supports one mode. And that is called a single-moded waveguide. And that's because the different modes travel at different speeds. So if we inject a signal at one end, and they're all synchronized, but we've excited different modes, if they travel at different speeds, by the time they get to the end, now our signal's all smeared and distorted because it's arriving at different times. And we don't like that. So we tend to pinch the waveguides down so they only support one mode. But if we enlarge the waveguide, then it supports multiple modes. And that's what we're looking at here. Here is a really neat phenomenon for doing a filtering function, but it involves a lot of what we've talked about. So it's called a guided mode resonance filter, and this is actually a very complicated device to explain, but I think you're in a very good position to understand how this works now, and I'm explaining this completely in terms of pictures. So the guided mode resonance filter, there's two phenomena happening at the same time. What we're looking at here is we have air up top. Down here, we have some kind of dielectric, and in this bar going across, there's even a higher refractive index dielectric, and so that guides a mode. And what we're looking at is a mode guiding along that dielectric left to right. Now, in and out of the screen, this would be of infinite extent. So we're actually looking at a slab waveguide here. We're just looking at a cross section of that. That's the first mechanism, waveguiding. There's another mechanism that happens in a guided mode resonance filter, and that is diffraction from a grating. We will have an incoming wave, which experiences a grating, and then it diffracts into multiple directions. So a guided mode resonance filter is when both of these things happen at the same time, and the diffraction grating and waveguide are close enough that they can interact electromagnetically. Let's break this down one step at a time. So we have a device that is both a diffraction grating and a waveguide. And we have an incoming wave. So that's step one. We apply a wave. The second thing that happens, we have a diffraction grating. So that incoming wave is split into multiple discrete directions that we call diffraction orders. Step three, under very, very special circumstances, one of those diffraction orders actually matches exactly to a guided mode. So rather than look like a beam traveling off in its own direction, it actually excites a guided mode and propagates along the core or the slab waveguide here. And we can still see a tiny bit of the other diffraction orders. Now, the step four, the fourth thing that happens, this mode that's being guided also sees the diffraction grating, and that diffraction grating makes it leak back out, right? So things are always reversible in electromagnetics. If the diffraction grating let light go into this waveguide, well, it also has to make light go out of the waveguide. And I'm saying light because this is generally used at optical frequencies, but this could work at any frequency. I've built these to work at radio frequencies. So we have light coming in, it gets diffracted under very special circumstances, that couples into a guided mode. If I were to change the angle or the frequency only slightly, it would no longer excite the guided mode. So this is kind of an easy picture to see this whole cycle, light coming in, couples into the guided mode, and leaks back out. But in reality, all of these overlap and are happening at the same time, and it's very difficult to look at this and see what's happening. So I had to break it up. But overall, this leaked wave and the applied wave combine and interfere to give an overall filtering response, which is quite interesting. So here are 6 different guided mode resonance filters, and they can look different, but they all have sort of this common thing. We have this overall reflection curve, and so for the most part, being dielectric, reflection is relatively low, but under these very special circumstances, there's a very, very narrow range of frequencies, or if you're an optics person, we talk about wavelengths, that produce reflection, and it reflects from this. And so it's kind of like a mirror that's only a mirror for one tiny, tiny frequency. And everything else, it just acts like a regular old slab of dielectric and reflects a little bit. And these little resonances, or these narrow reflection bands, are very narrow because it's a very special thing and a very difficult thing to couple that wave coming in into the guided mode. So anytime we need a very, very narrow filter, we like to use these guided mode resonance filters. Filters. What is a filter? Well, signals, waves, they're usually made up of a bunch of different frequencies or even a continuum of frequencies. And very often we would like to remove some and keep others. Whenever we do that, we call it a filter. And there is a million different ways in electromagnetics that we can make filters. Let's talk about some of them. Maybe one of the most famous is something called a frequency selective surface. So in stealth aircraft and stealth vehicles, one of the things that can make them stealthy is something called a frequency selective surface. These are typically arrays of metal elements that when a wave hits that, it interacts with the elements in a way that reflects some frequencies and transmits others. So, and that's what I'm conveying by color here. I'm trying to convey different frequencies here. And so this particular surface would pass the green frequency, but not the red or the blue frequencies. So maybe the bad guy's radar is green. And so when that hits the aircraft, that's actually allowed to pass into the aircraft where it can get absorbed. Probably right behind that is what would be called a radar absorbing material or a RAM. And all the others would just simply reflect. There are thin film optical filters. Probably one of the best examples is the oil on water. Have you ever noticed the rainbow kind of patterns that you see? And we can use that effect. It's a very thin film on top of water. The oil spreads out and it forms this filtering. And it's also angle sensitive. And that's why you see rainbow patterns, because the light in your eyes, you're seeing it at a different angle. Well, we can use more than one layer and do some really cool things. And here we have different colors for optical filters. That's pretty neat. Here is a simulation of a thin film optical filter. So the white regions on either side, that would be air. And here's a stack up of different layers. And by the way, it's very common for these thin film optical filters to have 100, 200 layers. You, if you're wearing eyeglasses, have these on your lenses, also on the lenses of a camera. There, it doesn't want to filter, but what it wants to do is prevent reflections. And there's several layers of different materials forming something. Now here, we're trying to filter a wavelength. What we'd like to do is transmit a wavelength around 500 nanometers, so that's green or something, and reflect everything else. Here's a simulation showing what would happen. So here's a pulse, and a pulse is composed of a bunch of different frequencies. And what happens is a wave comes in, some bounces off that first interface, but most of it goes through. Some of that bounces off the second interface, but most of that goes through. And it keeps reflecting off these surfaces. Well, then the reflected wave goes backward, and it reflects off these other interfaces. And this happens millions of times all over the place, and it's rather messy. And that's really what you saw in this simulation happening. But overall, we get this filtering response. And that's what's happening in a thin film optical filter. Let's go ahead and watch this one more time. So our wave comes in, notice it just bounces around and goes crazy. And there's literally millions of reflections happening here at the same time. But overall, we get this nice filtering response. Here is another neat phenomenon that can be used for filtering, and it's called directional coupling. What we're looking at here are two waveguides. These are dielectric waveguides, so the mode guided by the waveguide sticks outside of it a little bit. And what happens is when we bring two waveguides that are very close so that the fields overlap, what will happen as that field propagates, it leaks into the other waveguide. Let's go ahead and animate this. So as the mode propagates, it slowly leaks into the other guide until it's 100% in the other guide. And then as it keeps propagating, it comes back. And in fact, we get a periodic exchange of power from one waveguide to the next. Now, the reason this can be used for filtering is because this is frequency sensitive. How long it takes to go from one guide to the other depends on frequency. So there's some ways that we can use this. One, without being really a filter, is just power splitting. Suppose we inject energy into this port and we have a signal traveling down this line, and now all of a sudden another line comes in close proximity. Some of the power slowly leaks out. The farther away this line is, the slower that leakage. And so this has been designed so that only about 3% of the power is coupled off. And this is a good way if you want to monitor the signal on the line, but you don't want to take away all of the power. And of course, if we made this longer or somehow did some things to make the coupling stronger, maybe we could do a 50-50 split, and that would be called a 3 dB coupler. Now on to the filtering. Suppose we inject a signal over here. Well, there's one frequency that will 100% jump over to the second waveguide. Other frequencies either won't get all the way over, or maybe they went all the way over, then they start coming back again. Point is, there's only one frequency that effectively gets into this other line. And then it jumps to the other line, the other line, and the other line. And we have this sort of cascaded amount of lines, and then we can control these distances and thicknesses to control which frequencies get through. Here's another way that might look. And here the line is sort of meandering up and down, but notice we're controlling the gaps here, and all that, it's tuning the filtering response by how much frequencies get through and how much do not. And so if you pop open circuit boards in your television or your satellite dish receiver, you'll see a whole bunch of things like that in there, and it's performing filtering. Antennas. Well, most of you probably know what an antenna does. It takes some kind of electrical signal on a circuit board and sends it out into a free space electromagnetic wave that can travel through air or the vacuum of space and be received by yet another antenna and detected somewhere else. And I think this is one of the closest things to magic that we can possibly get, where we can talk to each other and send images without being connected at all. I think that's really cool. Here's just some types of antennas. There are many others, but these are the ones that you probably have seen. If you've looked at an old television, you've seen these two little wire antennas coming off, or more in modern days with digital antennas, you might have seen these sort of loop antennas. Maybe on top of buildings or power lines, maybe you've seen antennas that look like this. And these are called aperture antennas. We can think of them as a waveguide where it just ends and so the wave leaks out. And it's called an aperture. That's a fancy word that us electrical engineers use for an area where a electromagnetic wave escapes from. So this would have a square aperture, rectangular aperture. And so these are called aperture antennas. Just think of it as a waveguide that ends, so the wave comes out. If you've looked on top of circuit boards, maybe you've seen patch antennas. So it's a little tiny circuit trace. There's an electrical signal coming down here. That electrical signal starts bouncing back and forth here, and that launches a wave. So patch antennas, they're not actually the best antennas, but they're really convenient because we can put them on circuit boards, and so that makes them cheap and very convenient. There's array antennas. Here we have 4 antennas cooperating. Here there's an array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'll call it 12. 12 antennas sort of all cooperating. And this is generally done to make the overall antenna more directive. A single antenna would tend to spread energy in a lot of different directions, but if we put multiple elements together, multiple antennas together, we can make that more directive. On this slide, I'm going to show you an animation that I think will make antennas a lot more intuitive, and it's what's called the detachment mechanism. We know that electric field lines will extend from one charge to another, and we know that when we inject a signal into an antenna, okay, it's inducing currents in some way, but how do those electric fields actually detach themselves from the antenna and become a free propagating wave. So what we're looking at here is a thin wire dipole antenna. So we have a feed. We have one wire coming in and extending out, forming the antenna on one side, and the other part of the antenna here. So when we inject the signal, we have a plus voltage and a minus voltage. And so the plus voltage will inject positive charges and the minus voltage will inject negative charges. What you're going to see here is these charges will enter the antenna and they will extend down the arms of the antenna and then reflect back. And both will do that. The negative charge will go down the bottom side and the positive charge will go up the positive side. And we're going to track the electric field line connecting those two charges. So that electric field line propagates to the right, but it always starts at the positive charge and ends on the negative charge. Now, when that positive and negative charge come back together again at the field, or at the feed, and then leave the source, that's when the electric field can pinch itself off, form its own loop so that it no longer has a start or an end, and then launches into this free space propagating wave. I think this is very analogous to what happens when you're blowing a soap bubble. So you're holding one of the little things that has the ring at the top and you're blowing the bubble and it gets larger and larger and larger. And then when the soap bubble closes itself off, it detaches from the little stick and the bubble floats through the air. And a similar thing happens here with antennas when the electromagnetic field launches itself. And we could take any antenna and step through the detachment mechanism. So I absolutely love this way to visualize how antennas work and how the fields actually detach themselves from the antenna. Well, real antennas don't just have a single charge, we have signals, and in fact we're launching a whole series of bubbles from an antenna, and it might look more something like this. The last thing I'll leave you with here is something called a phased array antenna. And you've probably all seen these big parabolic dish antennas, and to steer them, we need these giant motors that have to move this thing, and it takes a lot of energy and it's slow. Well, what if you have a large antenna, but you want to steer it very, very quickly? Well, to do that, we want to eliminate all moving parts. And so here's a typical phased array antenna of what that would look like. No moving parts, but it's composed of a whole bunch of little tiny antennas. So what I've done over here, I've drawn a small array of little tiny antennas, these little orange box looking things. Each one's an antenna. And I'm feeding it with a signal. Now notice what I'm doing. All I'm doing is controlling the delay of these signals as they enter each one of these antennas. So just by controlling the delay, I'm actually able to steer this beam. So all these little antennas are acting like one big antenna, but I'm able to steer the beam. Now, since there's no moving parts and all I have to do is control the timing, I can steer this very quickly. Even more cool, I can steer multiple beams at the same time. So this whole concept is called beam forming and beam steering. It's also related to how holography works, which is kind of cool. So phased array antenna is very neat.